All right, so here we have eigenvalues and eigenvectors. So another way for mathematicians to boil it down to a single number with useful properties is an eigenvalue. And basically, this time we're looking at multiplication. So here we're going to say if I take a matrix and multiply it by a vector, that's going to be the same thing as multiplying a number, which we're going to call the eigenvalue, multiplied by a vector. But it's not any vector. These are called eigenvectors. And basically, what an eigenvalue, an eigenvector are is like if I multiply a vector in a very particular direction, it acts like a very particular number, right? Lambda. And so if I had an eigenvector of 1, 1, that means if I have a vector in this direction and I had an eigenvalue of 4, multiplying A times our eigenvector would be the same thing as just multiplying the vector by 4. And so it's kind of a way of saying in this direction, the whole matrix acts like 4. It's kind of what it's saying. And so how do we solve this? Well, we just use the following steps here. So we're going to just find the determinant of A. We're going to find the determinant of A minus lambda times the identity matrix and set that equal to 0. Notice that this is the same as this, but all I've done is moved everything to one side because lambda I, this is equal to lambda I, where I is the identity matrix, V. And then if I minus that from both sides, I'll have A lambda B. And then I can left factor out for the associated process 1 minus I, or 1 minus lambda I, the eigenvector. And that's how you get to this equation. Okay, so these are really the same equation. Of course, I'm writing on the wrong layer, so I'm just going to make a lot of notes. And then, so the first thing we're going to do this, it's going to pop out a polynomial, right? Equation. We call this the characteristic equation. And then we're going to take for each of the lambda values, we're going to solve for a lambda. Eigenvalues, eigenvalue lambda, we're going to solve for an eigenvector, B sub lambda, right? Each eigenvalue has its own eigenvector and you can't interchange it. So the value we find for the eigenvalue subscript 1 will be the same thing for this. And I use this notation. I'm probably the only one who really uses this notation. It's a tad pedantic, but I want to be very, very, very clear with you guys that this is connected to that, right? So in this class, I use that. When I teach my advanced matrix class, I don't use, I guess I do because I'm just so used to it, but I don't worry about it. So let's look at this one. Let's find the eigenvalues and eigenvectors of this. So here, if we're just going to kind of guess what the eigenvalues and eigenvectors are, let's just kind of look at multiplication real quick. So let me just guess the answers. And notice here that if I multiply by something that has like a 1 here and a 0 here, what does this look like? Well, this looks like 3 times 1, 0 times 0, 0 times 1, and 2 times 0. So this is just going to look like 3, 0, right? Or in other words, 3 times the original vector. Okay. And so now, how did I know that? Well, that's because I've done this for 1,000 times, right? But notice here, this is our goal. Our goal is to find things that look like this, right? So this, the matrix A times some vector, is equal to some value times some vector. And so I kind of wanted this, you see what our goal is before we attempt it. So let's actually attempt to do our goal. So let's do this slowly at first. So that we're going to take the determinant. So we're going to have A minus lambda I. Well, what is that? In this case, it's going to be 3 times 0, 0 times 2. And then we're going to have minus, and then we're going to have a lambda, and then we're going to have the identity. And notice that this I will match whatever size this is, right? It's by design. We're going to choose it to be that way. So we have this, we do this multiplication, and we're going to get 3 minus lambda, 0, 0, 2 minus lambda. Now, do you do this step every time? No. No, you almost always start here, right? You say the determinant of a minus lambda I is equal to this, and then we find this determinant. Well, here, if I compute this, I'm going to have 3 minus lambda times 2 minus lambda minus 0 times 0. So this will be minus 0 equal to 0. So I have 3 minus lambda, 2 minus lambda. Oops. Lambda equal to 0. Okay. So this is what we call, this right here is the characteristic equation. Okay, so this is our characteristic equation. So here we have our characteristic equation. So the roots of this equation are, of course, 3 and 2. And we just arbitrarily call one lambda 1, the other one lambda 2. Does it matter? No. But it's what you do, once you choose them, they're stuck that way. So now that we've chosen them, so this was step 1. Step 1 was to find our eigenvalues. So we find the determinant of this, set it equal to 0, find the roots, we got here. So that's step 1. Step 2 is we're going to do the following. We're going to solve this equation for lambda equals 0. So let's go ahead and do that. So here, if I do this, I'm going to have, so we're going to take right here lambda 1 equal to 3. So I'm going to do lambda 1 equal to 3. So step 2 for lambda 1 equal to 3. So now I want to solve this equation. Well, here I'm just going to plug in what I know these values are, right? So I'm going to have 3 minus 3, 0, 0, 2 minus 3 times some vx, some vy, right? I'm just going to label them vx, vy. In fact, oh, these aren't vectors anymore. In fact, just to make our lives easier, let's just call this x1 and y1. Okay. We'll just call this x1 and y1. This will be our v lambda 1. And here I'll have x1 and y1 to represent that equals to 0, 0 vector. Okay, so what is this saying? What is this? I should have probably had more room for this. What is this? Well, this is nothing more than a system of equations, right? So if I actually crunch through this real quick, so this implies that, well, 3 times 3 is, so this implies 0, 0, 0, minus 1, right? Times x1, y1 is equal to 0, 0, right? But if I did the multiplication of that, that implies that 0x1 plus 0y1 equals to 0. And this is 0x1 minus y1 is equal to 0, right? So if I actually computed this multiplication, I get this system of equations. Correct? And so that's why we needed, so in this, we're going to put together everything that we've used before. So I have a system of equations here. So I'm going to do it what I call the long way for the first one, and then I'll show you the short way for the second one. So the long way, I'm explaining every single step, why this goes here, why this goes here, why this goes here. Then we'll do it shortly, and then we'll review it real quick, and then we'll do it for a non-trivial example. In math, we would say this one's trivial, because you could say what it is. All right, so what happens here? So what must be true? So x1, 0x1 plus 0 y1 gives us 0. Does this tell us anything? No, it says 0 equals 0. That's literally all this says, right? If I was going to put this in my augmented matrix form, this would look like 0, 0, minus 1, 0, 0. Okay. So what is this saying? Well, this says nothing equals nothing, but so X here is a free column, right? I can choose it to be anything, right? Y here is not free, right? Y has to be 0, right? In order for -1, in order for this to zero out, Y1 better be 0, right? Everyone see that? Any questions on why Y1 has to be 0? No, because if I have nothing plus minus something and that equals 0, that something better be 0. So here, but my X can be free. So I'm just going to choose. So X1 here is free. Oops, free. Where now? X1 here is free. And so I'm just going to choose it to be 1. And so then I'll get X1 equal to 1, Y1 equal to 0. And so I can get my vector of lambda to be 1, 0. Now, is that what we got before? Yeah. Notice that these two match, right? So here I have the eigenvalue of 3. And then here I have my eigenvector. So my lambda, my first eigenvalue, and my first eigenvector, which are connected, right? So we get this. All right. So this is the long way of doing it. Let me show you the short way, but I've unfortunately ran out of space. So let me just open up a new one real quick. Hi, let's just open up a blank page. Let me rewrite a couple things. So here we have, wow, let me zoom on in so it doesn't look like hot garbage. Sorry about that. I ended up explaining more than I usually do. So here we have this as a matrix. So we're going to do step 2 again. But this time we're going to do it for lambda 2 equals to 2. And what you almost always do in this case is you just write out, you just skip straight to the augmented matrix. You just skip straight to it. Okay. This will always be 0. This will be your matrix where you just minus the lambda, you minus whatever this value is across the diagonal. This implies that you get 1, 0, 0, 0, 0, 0. Here, if we solve this, my y column is free, but x must be 0, right? X must be 0. So here, I'm going to set x2 has to be 0, right? Because that's what this says. This has to be 0. My y2 is free. And so I'm going to set that equal to 1. Okay. I set this one equal to 1. And so here I get the lambda for 2 will be 0, 1. Okay. And so here we have our two eigenvalues and our eigenvector. And notice this works. Notice this works. So let's say I have 3, 0, 0, 2. And notice that I chose it to be 1. Could I chose this to be, I don't know, 6? Yeah, that would have been fine too, right? So these are unique up to a constant in the sense that it can be any multiple of this. And so let's actually just do this, 0, 6. Let's just pretend it was 6 for a second. If I multiply this across, I get 0, or 3 times 0, which is 0, and 0 times 6, so that's 0. So I have 0 up top, and I'll get 0 times 0, which is 0, and then 2 times 6, which is 12. But notice this is equal to 2 times my original vector. Oops, make that look like a, there we go. Okay. And so what are the eigenvalues and eigenvectors saying for this matrix in particular? Well, in particular, I say if I'm in the x direction, right? If I'm in the x direction, this matrix acts like just a 3, right? It just moves you in 3 in that direction, right? And if I'm in the y direction, notice here, in the y direction, my vector in the y direction, it looks like I'm just moving that vector. This whole matrix just looks like I'm multiplying by 2. Now, if I'm in any direction in between that, it doesn't work out that way. However, but in those two particular directions, it does. And this becomes very useful for solving differential equations. And so 90% of the time, this is how you're going to solve step 2. You just throw it into the augmented matrix. Okay. If it seems kind of weird and odd, we'll do this a couple times and it makes a lot more sense. But the only way to learn how to do eigenvalues and eigenvectors, and I promise you this, is just to crunch through a couple of them, right? And just suffer through it. And I didn't really understand how to do this until grad school, which is like the world's biggest mistake, because I always just got away with my calculator. My calculator did it now. I was sitting there taking master's exam, and it says take the. I knew I need to take an eigenvalue, but it was a calculator-free master's exam. It was like, oh man, you've made mistakes in your life. That's what I told myself. You should know how to do this. So let's go ahead. Let's do this all over again for this. I'm going to go, since this is less trivial, we're going to go slow. I'm going to go nice and slow. All right, so our first
Hello,
step.
Professor.
Yes?
What if you're given a eigenvalue, given lambda? What if you're given a lambda for one of these problems? Because in the homework is like that.
Oh yeah, so the homework usually, so what the homework does, if I remember right, let me look it up. Hold on, let me open up the homework so I can answer the question correctly. Hi. Booko. Hi, book. If you're given an eigenvalue and it wants you to find the eigenvector, just skip straight to 2. If you're given the eigenvector and it wants you to tell the value, just perform the multiplication and then factor it out. Does that make sense?
Kind of. So if you're given the eigenvalue, you just do it just like we did.
Yeah. So let me get what's in chapter 8. And don't get me wrong, I like this book per se, but it's a great book to relearn all this stuff, not to learn it for the first time. Does that make sense?
Okay.
It's let me open up. Let me see exactly what you see in your homework. Hi, chapter 14. Yeah, we're not doing chapter 14. Not in this class, anyways. We might do it in the next. If it goes to 432, I'll also teach that. We might get there. A lot of complex analysis. You thought complex numbers were funny? Take that class and you'll start to learn. Almost surface integrals. No. All right, we're almost there. Sorry. Hi, we hit this chapter. Hit 2. Aha, here we go. It's Markov process. Nope, that's delayed too. I want the 8-1 homework. Aha, here we go. Oh, for like 11, it gives you one of them, right?
Right. That's
so
it.
Find the corresponding. I don't know why it just randomly gives you one of them randomly. It's fine. It would come out in the watch because if you know one, you know the other ones, right?
Oh, I guess.
It says find the eigenvalue, and then find the corresponding eigenvectors. Used for problems 15 and 12. I don't know why it's given it to you. Just because you have to calculate. You just have to calculate them all and do them all.
Okay, but I was just wondering because I was looking at that and like, wow.
It says find the eigenvalues and corresponding eigenvectors for all these. Use the given. I guess in problem 11 and 13 or 11 and 15, just find the one eigenvalue for it. Okay. So find the one eigenvector. Just skip to the end, I guess.
Sure.
The only reason I can think to give it to that. I will. Are we going to talk about complex analysis in this class? No. We don't get to it. That's 432. All right, so step 1. So step 1 is to take the determinant of 1, and then you're just going to minus lambdas across the diagonal. So here, just write out your thing, minus 1s across the diagonal. Okay, so we do this. That's my first step. You're going to just take this, you're going to take this determinant, and then you're just going to minus the lambdas across the diagonal. So we are doing this step right here, but we're just skipping right to what it means, right? we're just skipping to what it means. And what it means is just take just minus lambda across the diagonals. Then here we multiply this across. I'll have 1 minus lambda squared minus, in this case, 5 and 6. So minus 30.
Excuse me?
Yes.
Isn't it 2 minus lambda?
Oh, you're absolutely correct. Thank you. Oh boy. I need that one. That's what happens when you write on the wrong layer. Thank you. So we here have 1 minus lambda, 2 minus lambda, minus 30. All right, equals to 0. And we set it equal to 0, right? So we set all this equal to 0, as we're doing here. Okay. So in short, you're just going to write, take the determinant and set that equal to 0. And this is our characteristic equation. So what are the zeros of this? Well, you have to do some more math. So we multiply this across. And so here I'll get, so we multiply it all out. Be plus 2, so be minus, so oops, still minus 20. Hi. Yep. So be lambda squared minus lambda, or minus lambda minus 3 lambda plus 2. Add it to that, refactor this. And we get x. Oops. I put an x here, didn't I? Teaching too many of the other classes. Lambda squared minus 3 lambda. So this factors into lambda minus 7. Hi. Why are you being so crunchy on me? And lambda plus 4. Let me get rid of my extra note real quick so it plays nice. It's being crunchy. Yes. All right, now get rid of it. Be less crunchy. Okay. Hey, look, it writes again. So here we have lambda 1 equal to 7, and we'll have lambda 2 equal to minus 4. All right, I'm going to do one of these with you, and then I'm going to have you guys try to do one on your own. And hopefully that will dig out everything that goes wrong, and so we can talk about it. All right, so we're going to do step 2. I'm going to do step 2 for lambda 1 equal to 7. I'll show it to you. So here, it's lambda 1 equal to 7. So we're going to solve this. I'm going to write what we're solving again. See how I erased it. Our vector equal to 0. So this is what we're solving. This ends up translating into 1 minus 7. 6, 5, 2 minus 7, 0. Then from here, we'll go ahead and crunch this through. So this would be minus 6, 6, and 0. This becomes 5. Oops, I said 5, did not write 5. Still didn't write 5. 5 minus 5, 0. And then if I complete a reduced row echelon form, this becomes 1, negative 1, 0, 0. And after, I think, this week's quiz or last week's quiz, you had to do everything by hand, right? I said, fill out.
Yep, unfortunately.
Yeah. Yes. After we've done that quiz, and that's why that quiz was left alone, you can always just do this, and I won't care. So you're allowed to do this for the rest of the term, okay? So just RREF. Notice that this row is a multiple of this row. It cancels out. You should have one way to check that if you've done this right is you need to have at least one column that is free, right? That has no leading entry. In this case, I have no leading entry here for my y1. So my y1 is free. Okay. So our y1 is free, and I'm going to just set that equal to hold on. So I'm going to set this as equal to, in this case, I set it equal to 1, right? And so if this is 1, what must x2? Well, here I can write this out. This is x1 plus, or no, this is x1 minus y of 1 equal to 0, right? And so what's the solution here? What must x1 be? Yeah, it should be 1, right? And so here I get my vector of lambda 1 is 1 for y1, and then this is also y1, just by solving it out. Okay. All right, so go ahead and try to do step 2 for lambda 2, which is equal to minus 4. So go ahead and try that on your own. I'll give you guys a few minutes to do that. I'm going to step away for 1 second real quick, and I'll come back and answer any questions you have. All right, once you have solution, just write it in the chat. And if you have questions, go ahead and ask. And I'll wait until like 3 of you have an answer. I'll write out the first step if you haven't done that yet. So here would be minus 4, so minus of 4 would be plus 4. 6, 5, 2, minus of 4 would be plus 4, or minus a negative 4 would be plus 4. And then you just have this system of equations. Hold on, let me double check my notation matches the book's notation because I highly doubt it does for this case. Oh yeah, my notation is quite different than the book's notation for this. Oh boy. What is it using? Yeah, they use the little x1s and little x2s. Oh, I remember which book does. Makes me like chew on shirts and foam at the mouth. it's using bold x2 as the vector, and then little x1 and x2 as the elements in that vector. Good notation will set you free. And sometimes I don't agree with the book's notation. Granted, they make big money and I don't, so what am I to say, right? Do anyone get solutions? Okay, so we got 2 solutions that look like that. And those solutions are correct. That's good enough. We'll move forward on those. All right, so I'm going to do mine a little bit different than you. So once we get here, right, if I wrote this out, this is 5 and 6, 5 and 6, right? 0, 0. But notice here I can instantly say that since these 2 are the same, I can just have 5 and 6, 0, 0, 0, 0, because I can just multiply 1 of this row, or negative 1 of this row to this row, and just zeros that out. And then here I have a free column, right? But what is this saying? This is saying that, let me write out what this is saying. This is saying 5 of x2 minus, or plus 6 of y2 is equal to 0, or 5 of x2 is equal to minus 6 of y2. Now, what can I choose in order to make this work out? And the reason I'm showing you how to do it this way is because I'm going to do this when we do systems of differential equations, just because I don't like fractions. So I'm going to choose y2 to equal 5 and x2 to equal 6, and that is a solution, right? Because all I need is a vector, which solves this, right? And so here will be 5, or nope, it'll be minus 6 and 5. Now, is that different than what's in chat? Because what's in chat is negative 6/5 and 1. Well, what's the difference between these two? A factor
5.
Yeah, a factor of 5, right? But notice I said they're unique up to a constant. That means that this one is really basically the same as this one. So either one you choose is fine, right? If you used REF, this is the answer you pop out. If you just solved it by hand, this is the answer you popped out. Now the truth is that an eigenvector is what satisfies an eigenspace is all such vectors. And so a span, so we say the eigenspace for lambda 1 is equal to the span of this, right? So it's the span of all these vectors. And if you remember what a span is, or if you've never seen it, because you haven't had linear algebra, which drives me a little bit bananas, but the span is, I can take all these vectors, and so I can multiply by a constant. So a1 times vector 1 plus a2 times vector 2, right? And so it's all such vectors which include this case, and since in this case it's only just this, it's just all multiples of this vector. So notice that for the eigenspace for lambda 1, what's in it? Well, 1 and 1 is in it, minus pi and minus pi is in it, 32 and 32 is in it. So all these vectors technically could have been eigenvectors because they're all in the eigenspace. So it's the set of all such vectors. For here, the eigenspace for lambda 2, and I just use an E, lambda 2, is the span of all vectors that look like this. Oops, I do not need the. And so this is the span. Are we going to get too much into it? No, not really right now. It's useful in the next section. Any questions on how I found either of these two eigenvalues or eigenvectors? Again, this is one of those things you just have to crunch through like 4 or 5 of them, and then you finally get into the groove of understanding what it is. It's kind of like doing the reduced row echelon form. First couple times you do it, doesn't make sense, but after you do it like 4 or 5 times, like, oh, I get the song and dance, right? All right, so let's just type this into Wolfram Alpha, because eventually you're just going to use this to find everything. Hey, I forgot my comma. All right, so if you just type in the matrix, it's going to want to give you certain things. And the certain things it wants to give you is the eigenvalues and eigenvectors. You actually just type in the matrix into Wolfram Alpha. You actually don't type in anything else. If you have a TI-89, you type in, it's like INGBC is the values. No, whatever, it's EIG, capital V, something is the values, and capital V, something else is the vectors. And you have to just know how to read your calculator. But since we're going to be doing this online, I'm just going to show you this right here. And so here we get lambda 1 is 7, and the vector 1 is 1, 1, what we got. And then here we got -4, and then here we got -6 and 5. And I'm doing something a little bit closer to what the computer will actually do to get that. It'll get into diagonalization and all this other stuff and condition number. Don't worry about that, right? So here's just the eigenvalue and eigenvectors. So let's do a 3 by 3. Let's do a 3 by 3. Hello. Here we go. All right. So let's do this nice and slow so I don't get anyone lost. All right. So the first step, so step 1, we're going to take the determinant of 4, -1, 6, 2, 1 minus lambda, 6, and 2, -1, 8 minus lambda. All right, so this is what we need to do. We're going to set this equal to 0. All right. So we're going to find this determinant. To do this, I am going to do a trick. I don't know if I've taught you this yet, and of course I'm not on the right state of mind. So here you can just copy the first 2 layers down. This only works, this is a trick they use in physics all the time, because most of your matrices will be 3-dimensional because you have to deal with, because you're just dealing, most of your matrices are representing 3D coordinates, so they're mostly 3-dimensional. And so here you can just multiply the products of the downs. So this, you can multiply this across, this across, this across, and then minus the products of the up, this across, and this across. Have you guys seen this before in order to find a determinant?
Nope.
No. Oh. I was taught a lot of my math from physicists here at UNLV, I don't know, many moons ago, right? And most of them, so a fair number of them, at least I learned from, had some study from Russian physicists, and so they just learned how to do everything really fast by hand. I'm like, I would just look at them, it's like, I can't do this. Right? So here, this works out. And the reason this works out, because if we look at right here, I'll go ahead and go nice and slow. This is multiplied by this, and once again, it's this by this determinant, right? Well, that determinant's here. It's this and then minus this, right? And then multiplied by that again, right? So it encapsulates that. Same thing would be for each one of these. And so if I crunch this out, I'm going to have 4 minus lambda, 1 minus lambda, 8 minus lambda, plus the quantity of 1 minus 6, so -1 times 6 times 2, plus the quantity of 6 times 2 times 1, minus the quantity of 2 times 1 minus lambda times 6, minus the quantity of 1, -1, 6, and -1 times 6 times 4 minus lambda minus the quantity of 8 minus lambda, oops, times 2 times -1. Oops. That should be -1. Sorry about that. All right. Or you could just chunk it through a calculator, and a calculator will give you a characteristic polynomial. I'm not going to go through the slow multiplication of all this. We'll both die of boredom. I'll just give you the answer when you're all done. So once you get this, you factor this, just run this through whatever calculator you have. You're going to have lambda 1 equals to 9. You're going to have lambda 2 is equal to 2. And then you're going to have lambda 3 is equal. Okay. All right.
Excuse me.
Yes.
For the first lambda, right above it, it says negative lambda squared. Is do we combine that with the 13 lambda squared, or is that supposed to be a cubed?
That should be a cubed. It's a copy error.
Okay. Okay, thank you.
Thank you. Every time I write something that's horribly wrong, just correct me. It's going to happen more than once. All right. So you're going to get these to be your eigenvalues. But notice here that lambda 2 equals lambda 3. And that can mean a lot of things. But let's just crunch through slowly. Let's just crunch through slowly the steps for each of these. So step 2 for lambda 1 equal to 9. You know what? Nah, let's just keep moving. I was gonna have you guys work through one. I was like, nah, let's keep moving. That way I can at least start 2.1 or 1.1 today. All right, so if we do this, we're just gonna, everywhere we see the 4, we're gonna minus the 9. So -1, 6, 2, 1 minus 9, 6, 2, -1, 8 minus 9, 0, 0, 0. If I crunch through that, that's going to be -5, -1, 6. I might lose my voice before the end of class, which would be fun. 2 minus 1, -1. All right. Then we're just going to put this in RREF, just chunk it through a calculator. I'm going to get 1, 0, -1, 0, 1, -1, 0, 0, 0. All right, so what happens here? So what happens here is Z1 is free, right? It's free, so we're just going to set, so it's free. We're going to set that equal to 1. If I set that equal to 1, Y1 is also going to be 1 because V1 minus Z needs to be 0, so that's 1. And so if I set that equal to that, I'm going to get my lambda value to be 1, 1, and 1. Okay. Where does that come from? What is this really saying? This saying x1 minus z1 equal to 0. This says y1 minus z1 is equal to 0, and I have 0 equal to 0. So just for kicks, I'm going to call z1 1. That means y1 equals z1, so that's 1, and x1 is equal to z1, so that's also 1. Now, if I said z1 was 8, this would be 8, 8, and 8. Okay. Notice these are unique up to a constant. All right, so let's look at step 2 real quick for the other one. So lambda 2, which is equal to lambda 3, which is equal to 2. So if 2 lambdas equal to each other, step 2 will be the same for both, right? So in this case, we're going to have 4 minus 2, -1, 6, 2 minus, 1 minus 2, 6, 2, -1, 8 minus 2, dot, 0, 0, 0. So this gives me 2, -1, 6, 2, -1, 6, and then 2, -1, 6. All right, so oops, I forgot. 0, 0, 0. So I don't need a calculator to get this simpler. I don't, right? This is the same as this is the same as this. So I'm just going to go 2 - 1, 6, 0, 0, 0, 0, 0, 0. So in this case, I have 2 free columns, right? I have y1 is free and I have z1 is free because there's no leading term. So in this case, what you need to do is we're going to say y1 is equal to an s, z1 is equal to a t. And I'll show you why we do when we have 2. We can't just arbitrarily just give it a number. If we have 2, we have to set 1 to one variable, 1 to another. So what do I have here? Well, let's actually write out these equations real quick. That way, let's give myself room. Let's write out these equations. So this says 2 of x2 minus y1 or y2 plus 6z3 or z2, sorry, is equal to 0 and 0 equals 0, 0 is equal to 0. So that means x2 is equal to 1/2 positive, let's move it to the other side, 1/2 positive y2 plus 3, no, this means negative, I move it to the other side, z2. And here we'll have y2. We're just going to set that equal to s, and then z2, we're going to set that equal to t. And so here, if I swap this out, this is now an s, this is now a t. So I'm left with the following vector, right? I have 1/2 s minus 3 t, s, and t. But if I split this up, pull out the s, so I'll have s times 1/2, 1 and 0, plus t times -3, 0, and 1. I get 2 different vectors. So this vector is different than this vector, right? And they're different in a very particular way, which you guys, if you've had linear algebra, you know that these are linearly independent. If you haven't had linear algebra, we'll cross that bridge a little bit later, okay? But right now, if you just say S and T, you'll be in safe. Now, how do I know? How do you determine it's a free column? A free column does not have a leading entry. Remember, when there's no leading entry in that column, that's when we say it's free. So this one has no leading entry. This one has no leading entry. This is my leading entry. And so this is my only one that doesn't. Okay. So here I have this. So I actually have 2 eigenvalues, right? Or 2 eigenvectors. So I call this lambda. So I call this usually b lambda 2 and then this b lambda 3. That's usually what I do. So this is my b lambda 2, this vector right here. And it's my b lambda 3. Okay. Now, are you guaranteed to get 2 different vectors? In the actual, in an actuality, you may only get 1 vector out of this, and it's called a degenerate matrix, and then it has problems. We won't do too much of the 3x3s, but I just want you to see that and kind of test with it for a little bit. Work through the homework. We'll try to work through the homework and bring a couple of these questions to me on next time, and we'll address them then. Okay.